Yay!
Yay! Okay, now we need to start calculating the moments of inertia for sort of real-world objects, because there aren't that many objects that are just collections of particles, right? So one of the real objects that pops up all the time is a rod or a stick, right? That's pretty easy. Just something that has a length and it has a mass. Now, to calculate the moment of inertia of this thing, it's not obvious how we're going to do this because, I mean, the moment of inertia, we said, is it's the sum of each little mass times the distance away from some point. The problem is, what mass are we talking about? The whole thing has a mass big M, let's say. So what we're going to have to do is, if we want to calculate the I about the left end, let's say, what mass do we use? Well, I mean, there's mass all the way along this thing. So we need to use the methods of calculus. So what we do is we chop this thing up into lots of little bits of mass, lots of little dm's. And each of these dm's, let's say, is a distance x away from the point we're interested in, from the left-hand edge. Okay, so we're going to sum up each of these little dm's times how far away it is, squared, from the axis, from the point around which this thing is going to rotate. Just like we did before for compound objects, it's just that now we have an infinite number of things to sum up instead of just like 2. So how do we sum up an infinite number of things? We're going to integrate. All right, so it looks like what we're going to have to do is do an integral all along this thing. So somehow we're going to have to integrate from 0 to L, because that's the distance away from the axis. All these little bits of mass, so integrate up all the dm's, and multiply them by r squared. There we go. This, in fact, is going to be sort of our starting point for a lot of these objects. So we're just going to add up all the little bits of mass times each one's distance from the axis. All right. Now you see the problem. I mean, there's an r squared in there, and there's dm. So there's 2 different variables. But what you want in calculus is to get everything in terms of one variable, so then you can integrate. So what I really want to do is change variables. I know that my r is supposed to go, or what I really want to do is integrate x along that length, right? So really, I mean, maybe it'd be a little bit more clear if this were, instead of r squared, that's like x squared, right? Just the distance away from the left. So let's change variables, because that dm needs to be written in terms of an x so I can actually do the integration. Here's the standard trick. Here's a neat way to do it. So how do I change from dm to dx? That's the trick. So I'm going to write down something that is true. I'm not deriving this from anything else. I didn't get it from a book. I'm just writing down a mathematical sentence that happens to be true. So here's what we'll say. And it's useful to sort of say it in words. So dm, what is that? A little bit of mass. So a little bit of mass compared to the whole mass ought to be like a little bit of length compared to the whole length. I'm just setting up a ratio. That ought to be true. Really what I'm saying is that the mass is uniformly distributed along the rod, right? That's really what that's saying. But that's just a ratio that ought to be true. A little bit of mass compared to the whole mass is like a little bit of length compared to the whole length. But see, now we've got it, because now you can solve for dm and plug that. So dm is just m over L times dx. And now just take this and then stick it right there. So then I'm going to have an integral in terms of x. So this is going to be 0 to L. Instead of dm, I'm going to have m over L. And those are just constants, right? So that just comes out front. So it's m over L times dx x squared. Okay, well, that's going to be pretty easy because the m over L, those are constants, that comes out front. And then I just have the integral of x squared dx. Well, that's pretty easy. That's just x cubed over 3, right? And then I evaluate it from 0 to L. So this is just going to be equal to m over L, x cubed over 3, evaluated from 0 to L. Well, if I plug in 0, I don't get anything. If I plug in L, this tells me that the moment of inertia about the left-hand end is, well, if I plug in L, I get an L cubed. There's already an L in the denominator. So I get 1/3 ml squared. There we go. So if you want to know the moment of inertia of a rod about an end, if you know its mass and its length, well, there you go. It's just 1/3 ml squared. Okay, now remember, it makes a difference where the axis of rotation is. We saw that with the compound object. What if we wanted the moment of inertia about the middle? So we're going to pin the middle of this thing, the middle of the stick, and rotate about the middle. In that case, how do we do that? Well, everything stays the same. The changing variables trick, that stays the same. The only thing that's any different is as you're integrating along, if now we want the midpoint, if we want this, if we want that to be the pinpoint about which this thing rotates, then those little bits of mass are a distance x away from that point. And when you get to the middle, that's 0, right? Those little bits of mass, the dm's that are really, really close here, if that's a little dm right there, that's got its distance away from the middle point is almost 0, right? So how do you take care of this? You take care of it in the limits of integration. So instead of the distance going from 0 to L, the distance ought to go from minus L over 2, right? If you're on the left-hand edge, you are L over 2 away from the center. But then the direction is important. Remember when doing when considering where the center of mass is. So L over 2 to plus L over 2 on the right-hand side. Now, it turns out for a moment of inertia, we're going to square it, so it doesn't make that much difference. But we still have to get the limits right. Okay, so everything else remains the same. This is going to be dm x squared. And once again, we use the same change of variables trick. So it looks like we're going to have m over L. We're going to have x cubed over 3 when we do the integral, except now the only difference is we're changing the limits of integration. Let's see what happens there. Okay, so this is going to be m over L, x cubed. Okay, so if I plug in the top thing, I'm going to get L cubed. 2 cubed is 8, right? Times 3 on the bottom, so 24. So it's going to be L cubed over 24. And then I'm going to have minus the thing on the bottom. But the thing on the bottom is a minus, and we're cubing it. So this is going to be minus a minus, so it's going to be plus L cubed over 24. All right. Okay, so that's just L cubed over 12. And then one of those L's cancels the one in the denominator. So what you get is 1/12 ml squared. Okay. This ought to make perfect sense. When you're trying to spin a stick about the middle, it ought to be easier to spin it than spinning it around the edge. You can just grab one, right? If I have, make sure I get in the frame. If I have this thing, it's easier to spin it about the middle than it is to spin it about one of the ends. So sure enough, this is what this is telling us. It turns out to be a factor of 4 easier. That's not maybe obvious. But this should make physical sense. So the moment of inertia about the middle of a rod is 1/12 ml squared. Moment of inertia about the left-hand end is 1/3 ml squared. Okay, so that's our first object.